Hello, everyone, and welcome to today's lecture. My name is Noah Kogut Levin, and I am a senior at Princeton High School in Princeton, New Jersey. This is the final lecture of a series of lectures about climate change that I have organized together with my two school peers, Ava Ramirez and Grace Boulding, who unfortunately were not able to be here with us today. Over the past 7 weeks, the series featured 4 different speakers who addressed a series of varied yet inextricably linked issues concerning global warming. These include today's lecture on sea level rise. The 2021 IPCC report by the United Nations, one of whose lead authors is none other than today's speaker, I'm incredibly excited to announce, determined that climate change is undeniably occurring today and is being caused by not just human activities, but by preventable human activities. One thing that has struck me since I started delving deeply into issues of climate change is how little people know about a phenomenon that threatens the very existence of mankind. Renowned author Jonathan Safran Foer has commented that the sheer magnitude of climate change has turned it into an unfathomable and abstract concept in our minds. We are unable to adequately process the full scope of impacts that we will experience as a result of global warming. Furthermore, it is a common belief that climate change is an event that will occur in the distant future, not in our lifetime. However, there are already millions of people being displaced by and suffering from climate change today. Indeed, this is a very urgent issue that every generation alive today will experience at some point and in some fashion. Even so, there are still many things we can do to prevent or minimize the consequences, which is why it's extremely important for us to learn what we can do to help and how we can replace our current habits with more sustainable ones. I hope very much that this lecture series has done and will do exactly that, and that people leave it knowing how to be better stewards of our planet, our only home. Before I introduce today's speaker, I would just like to give you a few technical details about today's event. The lecture will last about 40 minutes, following by a 20-minute Q&A session. We ask you to please submit your questions using the Q&A function at the bottom center of the Zoom window on your phone or computer screen. The lecture will also be recorded and subsequently posted on YouTube for public on-demand viewing. You will be able to find the link to the recorded lecture on our website. I will post a link to the website in the chat, and the link can also be found on our Instagram page, climate_Princeton. Thank you very much for joining us. It is with great honor that I introduce today's speaker, Professor Robert Kopp, a climate scientist and a professor in the Department of Earth and Planetary Sciences at Rutgers University. He is also the co-director of the University Office of Climate Action. Professor Kopp received his undergraduate degree in geophysical sciences from the University of Chicago and subsequently went to Princeton University, where he served as a postdoctoral research fellow for science, technology, and environmental policy. He completed his PhD in geobiology at Caltech following his fellowship. Professor Kopp was a lead author of the 2021 IPCC report, one of the biggest reports ever conducted on climate change. He was also a lead author of the US Global Change Research Program's 2017 Fourth National Climate Assessment, a federally mandated report about the science of climate change focused on its impact on American society. Professor Kopp's research focuses on the uncertainty of climate change, with a heavy emphasis on sea level rise, which is what today's lecture will be about. I know I speak for my co-organizers of this lecture series when I say that we are very grateful that Professor Kopp has generously agreed to share some of his research with us. I can imagine you all are as eager as I am to hear what Professor Kopp has to say and about this topic. And so, without further ado, I hand him the floor. Thank you.
Great, thank you, Noah, and thanks to all the people who are attending this Saturday evening. We're going to talk today about sea level rise, but I want to start with just a little bit of background on climate change as a problem. I know you've been going through this lecture series over the last couple months, so this may be familiar to you, but let's start where we are. So, as you probably know, we're at an unusual time in Earth history. For over 800,000 years, carbon dioxide concentrations in the atmosphere have stayed between around 180 parts per million during periods we call ice ages, when ice sheets in North America extended down to northern New Jersey and New York City. and periods of up to about 300 parts per million during warmer periods called interglacial periods, where there were no large ice sheets in North America or Europe. And you can see that in this curve here, these are carbon dioxide concentrations reconstructed from bubbles of air trapped in cores of ice. You have this sort of jigsaw pattern, those low ice age values, warmer and higher interglacial values, up and down, and so forth, up until about 100 years ago, or 150 years ago. In 1913, carbon dioxide concentrations surpassed 300 parts per million. And spring 2014, just about 8 years ago, they surpassed 400 parts per million for the first time in well over 800,000 years. And they're going to remain above that level for all of our lifetimes. So let's look at that a little more closely. So 1750, before the start of the Industrial Revolution, carbon dioxide concentrations in the atmosphere were around 277 parts per million. 100 years later, they had climbed to 287 parts per million. Over the next 50 years, they climbed a comparable amount to 296 parts per million. And by 1950, they were at 311 parts per million. And then in the post-World War II air period, we see what's often called the Great Acceleration in a whole wide variety of economic and environmental parameters, including carbon dioxide concentrations. Between 1950 and 1988, carbon dioxide concentrations climbed to 351 parts per million. And 1988 is a significant year because that's when some of the most famous congressional hearings on climate change were being held with Jim Hansen and Al Gore. Now, in 2021, about a little over 30 years later, we're at 417 parts per million. So one thing you should notice is that most of the increase in carbon dioxide concentrations above the pre-industrial level has happened since the late 1980s. So even though people, like scientists like me, like to talk about climate change as a problem of the industrial era, really it's a problem of the last 35 years. Most of the problem has happened in my lifetime. And why is that? It's because most of the fossil carbon dioxide ever emitted has been emitted over the last 30-some years, basically since the end of the Cold War. This plot here, which starts in 1750, is showing you the cumulative amount of carbon dioxide emitted from the start of the Industrial Revolution by the burning of fossil fuels. So between 1750 and 1850, a total of about 5 gigatons, or 5 billion tons of carbon dioxide were released into the atmosphere by the burning of coal. Between 1750 and 1900, mostly still burning coal, starting to bring in a little oil too, we get to about 45 billion tons total, so 45 billion tons emitted over 150 years. Between 1750 and 1950, about 230 billion tons of fossil carbon dioxide had been emitted. And between 1750 and 1991, just before the UN Framework Convention on Climate Change was signed, 830 billion tons of carbon dioxide had been emitted. In 2020, cumulative emissions reached 1,690 billion tons. So about as much between 1991 and 2020 as between 1750 and 1991. So again, even though there is a long legacy associated with the entire Industrial Revolution, really most of the climate problem has been created in the post-Cold War period. And as a result of these emissions, our planet is running a fever. This plot here is showing you average annual global temperatures from the 1880 to 2021. And what you see is that between 1980 and 2020, and 2021, temperatures rose at an average rate of about 0.2 degrees Celsius or 0.3 degrees Fahrenheit per decade. In 2020, the average global temperature was about 1.2 degrees Celsius or 2 degrees Fahrenheit above the late 19th century average. And the last 7 years are most likely the warmest 7 years on record. Now, we're here to talk about sea level. Since the early 1990s, we've been able to measure sea level from space using instruments like on satellites like the one showed here that basically bounce radar off the surface of the ocean and measure how long it takes to come back and use that to determine the height of the sea surface. And so if we look at this satellite altimetry data, here is a map from the 2017 National Climate Assessment. What you see is that sea level is rising at different rates in different places. very fast, for instance, over here in the Western Pacific, pretty slowly in the Eastern Pacific. But on average, if you look across the whole world, there's a clear global trend. Global average sea level is rising, and it's rising at an accelerating rate. In the early 1990s, sea level was rising on the global average level about 1 inch per decade. Now it's rising closer to about 1.6 inches per decade. And we can put this in longer term context using two types of records. One are sort of direct instrumental observations of the height of the sea surface at specific points using an instrument called tide gauges, which are basically, you stick something in the ground, you have a floaty thing, and you measure how high the floaty thing is relative to the fixed point in the ground. And the tide gauge records go back in much of the world, many coastlines, to the middle of the 20th century. And then some of the oldest tide gauge records come from Northern Europe in the 18th century. And we can go back even further using geological records. Over here on the left is a photo of a field team led by my collaborator, Ben Horton. So I think this is a salt marsh in Newfoundland, but you can find similar salt marshes along the Jersey shore. And what geologists do is take cores of sediment from the salt marsh and look at the fossils of organisms, tiny organisms called foraminifera and diatoms in the core. And by looking at those populations, you can figure out where in the tidal zone different layers of sediments were laid down. So you combine that with something like carbon-14 to determine how old each layer is, and you can reconstruct sea level at a sort of 10 centimeter or so scale going back a few thousand years. Over here on the right, this is a picture of the site of the Battery Tide Gauge at the southern tip of Manhattan. You can see the Statue of Liberty in the distance there. So one of the things our research group does is use statistical and geophysical models to piece together these records. So even though we don't have before the 1990s this global coverage that satellites give us, but we have these measurements, both geological and instrumental, of sea level at specific points along the coast. And so we have to do some modeling to infer from these limited set of points what global sea level was doing, but we can do that. And this is a curve we get. This is global average sea level going back about 3,000 years. So the green part is derived from the geological records, the gray from tide gauge, purple is the satellite record. And what you see is something that Barack Obama tweeted about when we published the first version of this curve in 2016. We're currently seeing in the 20th century, we saw the fastest rise in sea levels in nearly 3,000 years. And in fact, additional work since our original paper was published gives us an extremely high degree of certainty that it's been more than 3,000 years since sea level rose at the rate it did during the 20th century. And it's, as I mentioned earlier, we're now more than 2 times faster than it was in the 20th century. And sea level is rising even faster here in New Jersey than in the global average, primarily because the land is sinking. Since 1911, sea level in coastal New Jersey has risen by about 1.5 feet, which compares to about 8 inches in the global average. This difference is due primarily to the fact that we are on the edge of where the giant North American ice sheet was. That ice sheet sort of pushed up a bulge around its edge, and that bulge has been sinking for the last 10,000 years, causing, and it continues to sink today, and that's caused about 7 inches of land sinking in our area since 1911. And in addition, on the coastal plain, which constitutes most of the Jersey shore, we are also pumping groundwater out from between sediments for use. And then when you pump the groundwater out, sediment sinks, sand sinks underneath that. So that's given us another 3 inches over this time. And this is having real effects today. As Noah mentioned, right, climate change and sea level change, these aren't problems in the future, they're problems for today. Sea level rise is making high tide flooding more common. So this is a photo of a high tide flood event near New Jersey. It's what's sometimes called a nuisance flood. You can see it's not causing the sort of damage that gets you federal aid, but it would indeed be a nuisance if that were your car over there and you couldn't get to your house. And the number of high tide flooding days in Atlantic City, which is typical of the shore, has increased from less than 1 per year in the 1950s to an average of 8 per year over the last decade. And this is a period over which sea level rose by about 9 inches, right? And pretty simple relationship, right? When you have higher average sea level, you don't need as extreme a high tide to cause one of these high tide flooding days. Sea level rise is also enhancing storm-driven flooding. If your average sea level is higher, it doesn't has bigger storm coming in to cause more extensive and more expensive flooding. Human-caused sea level rise was responsible, based on work we've done with Climate Central and Princeton and in the Stevens Institute of Technology, was responsible for about 13% or about $8 billion of the property damage caused by Hurricane Sandy in New Jersey and New York in 2012. And about 70,000 people were exposed to flooding during Sandy who wouldn't have been exposed had it not been for the human contribution to sea level change. So what's driving sea level rise? Well, in the global average, there are two main processes. One is the melting of ice on land and ice sheets and glaciers, and the second is the expansion of the ocean as it warms up. Shrinking ice sheets and glaciers, this is a photo of from the Greenland ice sheet, are responsible for about half of the 3 inches of global average sea level rise that occurred from 1993 to 2018. Over the period from 2006 to 2018, there was about 1.7 inches total, 51% about, according to the IPCC assessment of that, was due to the melting of glaciers and ice sheet. The expansion of the ocean as it warmed was responsible for most of the rest, about 34% of the total. And then there was a small contribution that has to do with the pumping of groundwater on land and letting it run off into the ocean. So that's about 15%. So that's the global average story, but nobody lives at the global average, right? We live here in New Jersey. And when we think about the sea level change we actually have to deal with, we have to account for the factors that cause local sea level change to differ from the global average. So here's an example from New York, from Atlantic City, where over the same time period that we saw about 1.7 inches in the global average, we get about 2 inches. And the breakdown's a little different. Only about a quarter of this is due to melting of ice on land. And that's because, if you think about an ice sheet or even a glacier, these are huge masses of ice. It takes 360 billion tons of ice melting to raise global sea level by 1 millimeter. And when you move such large masses of ice around, you do things like change the Earth's gravitational field and change the Earth's rotation. And as a consequence, if the Greenland ice sheet melts, when the Greenland ice sheet melts, you actually get a sea level fall right near the ice sheet because you've reduced the gravitational attraction of the ice sheet. And you get a below global average sea level rise, sort of in the slightly further afield area, and above average farther away. We're relatively close to the Greenland ice sheet. We're relatively close to the Alaskan glaciers. And as a consequence, we get a little less sea level rise from those than the global average. About a quarter is due to changes in density of the ocean. And then we have two new factors, or three new factors. So one, the vertical land motion, which, as I mentioned, is the dominant driver over the last century for why we're seeing more sea level rise here than in the global average. And then we also have both the land water storage that I mentioned, but also changes in ocean circulation and winds. And these together are responsible for about a quarter of the picture here in New Jersey as well. So these are all the things you have to think about if you're trying to plan for sea level rise. You got to take into account the factors that cause local sea level change to differ from the global average. So what can we anticipate in the future? Well, there are a few factors which cause a fairly large range of future projections. And one of the key drivers is a range of possible human emissions. So here, this is a plot of global carbon dioxide emissions from both fossil fuels and deforestation, starting in 1960. And I know it was before many of you were born, but I want you to think back to the 1980s. Right? So as I mentioned, since the start of the Industrial Revolution, human had emitted total of, by the early 80s, about 600 billion metric tons of carbon dioxide from fossil fuels. And together with deforestation emissions and other greenhouse gases, these have raised global average temperature by about 0.4 of a degree Celsius or 0.7 of a degree Fahrenheit. Suppose we had had a policy change, and starting in 1992, the year when international climate talks first began, we had gotten global carbon dioxide emissions on a downward trajectory. We could have had about 90 years to get global emissions to zero and still had a good chance of stabilizing the climate at well below 2 degrees Celsius or 3.6 degrees Fahrenheit, which is one of the international goals agreed to in the Paris Agreement signed in 2015. The trajectory shown here would have likely led to a total of about 1.8 degrees Celsius of warming or 3.2 degrees Fahrenheit of warming by the end of the century relative to the 19th century. But we didn't get at that future. Instead, carbon dioxide emissions continued climbing. And now nearly 40 billion tons of carbon dioxide are emitted from into the atmosphere each year. As a consequence, the planet's temperature has increased by about 0.8 degrees Celsius since the mid-1980s. And we are feeling the consequences I talked about earlier, as well as other consequences like more intense heat wave, more intense precipitation. So let's talk, by contrast, about another future, what 15 years ago we might have called business as usual. If over the last decade, emissions had continued growing at the same rate as they did in the first decade of the 21st century, we would be on something like the trajectory shown here in red, on track for about 4 degrees Celsius or 7 degrees Fahrenheit of warming by the end of the century. Instead, and this is good news, emissions growth has been slowing as a result of a combination of policy and the market-driven retirement of coal and the growth of renewable energy. Now, this is important to realize. We may not have had as aggressive policy as many of us would have liked to see, but there has been a lot of progress. In the US, the Clean Power Plan, the Obama-era plan from just 7 or 8 years ago to regulate carbon dioxide emissions from electricity never went into effect, but we already met by 2020 the emissions reduction goal that the Clean Power Plan set for the electricity sector by 2030. Good news there. So we're no longer on this red course, the old business as usual. So it is now still possible to achieve the Paris Agreement goal of limiting warming to 2 degrees Celsius. But instead of getting to zero in 90 years, we have about 30 years to do it. And alternatively, as shown in the pathway here, we could take a little longer and hope that we have the right technology and land use policies in place in the last quarter of this century so that humans are actually actively sucking more carbon dioxide out of the atmosphere than we're putting in. And then here's another future. This is the future that's closest to current policy, which puts us on track for about 3 degrees Celsius of warming, about 5 degrees Fahrenheit of warming by the end of the century. Whichever course we're on won't affect how the climate changes over the next decades. The benefits of reduced emissions in terms of things like more intense heat and more intense rainfall will start to accrue in the 2030s. And the sea level differences won't emerge until the second half of this century. But the world in these two futures, the current policy and the 2-degree world, nonetheless look very different. But these projected, but that's just one source of the spread of uncertainty. Another key driver of the range of projections is the incomplete and rapidly evolving scientific understanding of how ice sheets in the ocean interact. So there are processes that the science is just learning about how ice shells with floating bits of ice on the edge of the ice sheets hold up ice sheets, how atmospheric processes can cause the loss of those ice shelves, and how without the ice shelves, ice sheets can advance more rapidly or collapse more rapidly. And that's just one of several different processes that are sort of at the cutting edge of scientific understanding and give rise to a spread of projections of how the ice sheets will respond even under a particular emissions scenario. So what are we looking at? Here are some projections from a report we did about 3 years ago from the New Jersey Department of Environmental Protection. Through 2050, here in New Jersey, we're likely looking at about 1 to 2 feet of rise, regardless of our emissions level. As I mentioned, the benefits of reduced emissions in terms of sea level rise really don't start to accrue until the second half of this century. But beyond 2050, the projected rise is increasingly sensitive to the level of emissions, especially for high-end risks, the risks that have to do with these behaviors of the ice sheets that we don't have great scientific understanding of right now. So under a moderate emissions trajectory, the one that's sort of most consistent with current policy, the most likely sea level projections is about 1.5 to 3 feet of sea level rise relative to the start of the century by 2070, about 2 to 5 feet by 2100. Whereas under that 2-degree compatible path, we're looking more at about 2 to 4 feet by the end of the century. with those higher numbers, including the possibility that the ice sheets might be on the more sensitive end of projections. So that has some significant effects, right? We talked about how the sea level rise we've already experienced makes high tide flooding more common, makes storm flooding more extensive and more expensive. What I want you to think about here is let's think about one sort of historic event. The event that the sea level height that back in 2000 we would have said had maybe a 1 in 10 chance of occurring in a typical year, what you might call a 1 in 10 year extreme sea level event. That was about 3.3 feet above the high tide line. Now, what happens if we're sort of on a current middle of the range of projections for current policy scenario? Well, by 2030, that 1 in 10 year event now happens an average once a year. So it becomes the annual maximum high water. By 2055, it's now the tidal flooding event, right? So we start to see this 1 in 10 year event from back from the year 2000, about 5 to 10 days per year on the shore. And by 2100, we've had so much sea level rise that what was once a 1 in 10 year flood is now simply high tide. So that's just gives you a sense of how changes in average sea level can lead to very rapid changes substantial changes in the frequency of extremes. So if you look at just the middle of the road projection, right, the high tide flooding levels, the one that used to happen, every couple of years back in the 1950s, are now happening more than a week per year. It happen a good chunk of the entire year by the middle of the century along the Jersey Shore. So that leads us to the last bit that I want to discuss before we get to discussion, which is what do we do about this? So in the adaptation toolkit, here are a few different options we have, right? So one is simply no action, right? You wait for a storm to come through and then you rebuild essentially unchanged. Maybe actually even you're a little gentrified because the storm has cleared out some of the cheaper housing. And you assume that the subsidies from the rest of the country that allow this to happen will continue indefinitely. What are those subsidies? Well, flood insurance is subsidized, and disaster relief is a transfer from the areas of the country that are not affected to the areas that are damaged. And that's a sort of solidarity that we should have as a nation. But it's also, if it keeps happening, you start to have to ask questions. And in any case, we're actually not doing a great job of working together to manage our climate risks right now. So we think in this country used to count on coming to one another's aid across the country in the aftermath of a disaster. And by and large, eventually we still do. But this process has become slower and slower. I want you to think back to Hurricane Maria back in 2017, right? A year later, New York Times says Hurricane Maria, after one Hurricane Maria anniversary, Puerto Rico is still in ruins. A year and a half later, the House and the president are still debating disaster relief and Puerto Rico aid. And it keeps getting held up by dysfunction in our legislative system, which is certainly not a problem unique to climate, but is sort of characteristic of our national governance institutions right now. Right? So September 2017 to May 2019, still debating disaster relief. And in fact, come to February 2021, there is still a whole bunch of appropriated disaster relief that had not made its way to Puerto Rico almost 4 years later, right? So this is not a sign of healthy governance and healthy disaster and emergency management. And this is the baseline upon which these climate factors are aggravating the problem, right? So we've got to, the solution of not doing anything is not tenable. So what are the other options, the more proactive options? Well, do we modify our communities to accommodate occasional flooding, right? Well, we're certainly doing that now quite a bit in New Jersey. Here is a photo from Manasquan, and you can see this gentleman has elevated his house, created himself a nice garage, protecting the base of the house from a lot of flooding. And the new sea level rise guidance for the state basically tells people that if you have major reconstruction, you've got to basically add in an additional 5 feet to count for sea level rise if you're in the flood area. But we do have to remember that individual action is not sufficient for accommodation, right? This guy might have elevated his buildings, but if we haven't made the investments in critical infrastructure, storm comes through, he might still be without electricity and sewers, and roads might be inaccessible. And so we still have, when we talk about accommodation, we have to think about collective as well as individual action. Do we build hard protective structures like flood walls? Well, this is something that makes a lot of sense in many areas where you have dense concentrations of people and property. So Manhattan, for example, this is the diagram for the East Side Coastal Resiliency Project, which is under construction now. And I said that there are many places where this may be your primary option, but you also have to remember that you need to plan for occasions when hard protection fails. Just think back to Hurricane Katrina, for instance, right, where New Orleans is protected by levees, but levees can fail. And when they do, if you haven't planned for that, it can be disastrous. Another option, at some point, do we say, okay, we have to relocate to higher ground? As some communities like Oakwood Beach and Staten Island, and indeed some communities, one of the neighborhoods in Rutgers, chose to do in the aftermath of Sandy, getting people out of harm's way. And then there is, additionally, the option of, in some cases, right, can we put in place salt marshes or other things that serve as natural barriers that give you some of that protection against wave energy? Right? These are all things in the toolkit. But there's a toolkit. There's no out-of-the-box, ready-to-go solution. Right? Figuring this out requires community engagement. It requires deliberative processes, and it requires thinking about sequencing, right? Because there's a broad range of projections for New Jersey, as I mentioned, even under the current policy scenario, current emissions policy, right? 2 feet to 5 feet, potentially even more under higher emission scenarios. Do you want to plan for the high end of that as though it were a certainty? Or do you want to take an iterative approach, trying to figure out how do you make sure you'll do okay if we end up at 5 or 6 feet without making those expensive investments, like, for instance, evacuating communities that might actually be able to live in where they are for another century prematurely, right? You need to think about sequencing. You need to think about what the periods, what the intervals of sea level rise, different adaptation solutions are, and when you switch to one to another. And this requires an ongoing iterative process of engagement between people who understand the system dynamics and the people underground whose problem it is. And that's one of the things we're trying to put into action at Rutgers through initiatives like our Coastal Climate Risk and Resilience Graduate Training Program, which teaches graduate students in the natural sciences, social sciences, engineering, and policy and planning to work with one another and with coastal communities, and actually helps coastal communities develop resilience plans. And this new project that we are leading, the Megalopolitan Coastal Transformation Hub, which is a National Science Foundation funded project that engages 12 universities, including Princeton, with 3 goals. One, advancing the understanding of how changing coastal climate hazards, changing coastal landforms, and human decisions, both at a household level, do I do nothing? Do I adapt in place? Do I leave? At a municipal level, how do those sorts of decisions affect my town's finances and our ability to provide services? And at a market level, how does the property market, the insurance market, the labor market mediate that? So we want to advance the understanding of that system so that we can better inform flexible, equitable, and robust long-term planning to manage climate risk in dense, sprawling urban regions like the New York City, New Jersey, Philadelphia region. So we will, over the next 4 years, be working with somewhere between about 3 and 6 communities in our region, both to develop a better understanding of the science and to help the communities actually deal with their problems. And in course of doing so, we want to build a model of academic stakeholder partnership that provides insights for just, equitable, and inclusive climate action in diverse coastal urban megaregions around the world. Our region has a laboratory that can inform the entire world. But whatever we choose to do, however we choose to adapt, the starting point is mitigation, right? There's that difference between what that 2-degree world with a more stable climate and the current trajectory, which gets us to 3 degrees of warming by the end of the century and more beyond, and sustain, faster sea level rise. So we need mitigation because it gives us more time to adapt, and it also deals with problems I haven't talked about. For instance, if we stabilize the climate, we stop making our heat waves worse. We don't reverse the damage we've already caused, but we can make things stop. By getting to net zero, we can make things stabilize. So I want to conclude just with a couple of things. So what does this mean for you? Well, ultimately, the most important thing you can do is act in your communities. This is not a problem that can be solved by individual action in isolation, right? Is not a problem that can be solved if you simply do something that reduces your carbon footprint and you do not use that as a stepping stone for catalyzing broader conversation. But what you can do are be active citizens, right? When you're old enough, you can vote. Even before you're old enough, you can engage in national politics. But equally important is being engaged in your local politics or state politics and in your work or school communities. Because as much as it would be great for the federal government to provide stronger policies, even if it does that, that's not going to be sufficient, right? We need to act at all of these levels. It's what sometimes called a polycentric system, right? So we need a broad-based approach that involves everybody, and that means engaging at these multiple levels. So some of these photos here on the right are from work we've been doing at Rutgers. As Noah mentioned, one of my roles is as co-director of our new university Office of Climate Action, and we are trying to mobilize Rutgers as the State University of New Jersey, as a community of 100,000 students, faculty, and staff with a $4 or $5 billion a year budget, trying to mobilize that so that we are making investments, not just in getting our own carbon footprint to zero, and not just in making our own communities more resilient, but in leaning into our missions as the public land-grant University of New Jersey and working with communities across the state and with the state government to advance the goal of a decarbonized, more resilient New Jersey, and to advance the goal of national climate stabilization, national decarbonization. So that's our goal. And I think many organizations can ask the same questions. What does it mean for our organization to contribute to the goal of national decarbonization by mid-century, which is the time frame needed to hit the Paris Agreement goals? And that's a large ask. So I want to give you something smaller to do too, but still a big project. For those of you who either rent or have parents who rent, or have parents who own their house, you own a bit. The owners own a bit of the nation's infrastructure, and your renters, you actually do have some voice as well. And I want to direct you towards this guide from Rewiring America, which it walks you through the steps of basically getting your home's infrastructure off of direct fossil fuel combustions and onto electricity, which is a key step, because we have the solutions to electrify, to decarbonize the grid. And so the more we can stop burning fossil fuels in our basements in order to heat our water and heat our houses, the easier it will be to decarbonize the nation's infrastructure as a whole. And with that, I want to thank you for your attention. Thank you for coming on this Saturday, and open up for discussion.
Thank you, Professor Kopp. That was a very inspiring and informative lecture. We have several questions here. I would like to start the Q&A by asking a few questions of my own. I have a question that I've been wanting to ask you. So one of my greatest passions is veganism and environmentalism. So you mentioned in your lecture that reducing greenhouse gas emissions is an important way to address sea level rise. Even if it's not reversible, we can still slow it down. I would like to give some context before I ask the question. According to the UN's FAO, animal agriculture alone emits more greenhouse gases than the entire transportation sector. And a 2020 study by the EPA and several universities, including Oxford and Stanford, found that emissions from our global food system alone will make it literally impossible to prevent a warming of 1.5 degrees and extremely difficult to prevent a warming of 2 degrees. And even if we removed all other emission sources. And finally, the 2018 Oxford Poor Nemesek study found that going vegan reduces food emissions by 73%. And so given this information, some people suggest that veganism is an effective way as an individual choice for people to address climate change and sea level rise, especially in Western countries where we don't depend on these animal products. And I would like to know your professional opinion on this and whether it's a viable option for people in these Western countries.
So I think that there's no silver bullet, right? So, that about 22% of global greenhouse gas emissions in sort of CO2 equivalent terms are due to agriculture, forestry, and land use. So that's the largest part of that is deforestation, and the second largest part are the guts of ruminants. And then also, rice farming is pretty up there as well. And a lot of that deforestation is driven by the agricultural sector, right? So this is, not a small chunk, but it is, it's not the whole life, right? So your wedge that you can possibly address through dietary impacts, if you did it at a global scale, would be about 15% of global emissions. So, I think it's certainly a very valuable thing to do. It's quite true that, basically every time you go higher up the food chain, you're having a more energy intensive diet by roughly a factor of 10. And so, eating lower on the food chain, and that does not have to be never eating meat. It just means shifting, because this is, from a carbon perspective, everything that you lower it helps, right? That certainly helps. But I also want to get back to the point I made about individual action, right? Individual action is great, but individual action, if it's taken as an individual act and not as part of a process of social change, is, some would call it a distraction, but it's basically, it doesn't get you there, right? So whether your individual actions are, cutting back on flying or cutting back on meat or putting solar panels on your house, right? Those only get to scale in as much as those individual actions are part of your process of being an active citizen, and are part of fostering national dialogue and national change on it.
Yeah, if you put individual action and collective action together, that's much more effective. Yeah. Thank you. That's a very informative answer. So I will start reading some of the questions. Someone asked, you argue compellingly for the urgency of collective response to the ocean rise challenge. Where does this leave the individual eager to be engaged with this issue?
So I think that's very much sort of a similar question, right? So one is you need to, our democracy is not in good health, and it requires you all to get engaged in order, frankly, for us to make it work again, right? And so, this is this is not just this sea level issue, this is sort of the broader climate issue, right? We know the technological solutions that we need to implement over the next 20 or 30 years. There's still a lot more we can develop, but we have the core solutions we can start with. We know policies that could work. What we don't have is sort of the political will to have made it happen, right? If we had the political will, right, we could have started in 1992 and been on this gradual downward trajectory. That has metastasized from being something that is a particular turn to climate, frankly, being something that particular current for the longevity and health of our democracy, right? I mean, if you look at how public health now is suffering from the same sorts of denialism and politicization of science that climate has been suffering for the last 20 some years. Voting is now contested science in the same way that climate change is now contested science. And so all of those need to be addressed. And so I think the most important thing you can do as an individual is participate in civic action and in electoral action to help get people elected and create a political environment in which we can start to fix our democracy. So I know that like as an individual, you have to be active as a collective. I think that's the core of it. We've got to fix our democracy. Beyond that, I mean, I think that the other things like these individual things that address your carbon budget, they're great, but they're, as I said, like that they have to get to scale, and the only way they get to scale is if they're linked to collective action. I mean, I'm still, if all you want to do is decarbonize, or you eliminate fossil fuels from your house, that's great. Even better if you want to tell people what you did and how easy it was to do it. So I think that's, I don't know that that's an entirely satisfying answer for somebody who doesn't want to engage in collective action, but the challenge is that big societal problems can only be solved by society.
Yeah, that makes a lot of sense. Thank you. So someone else asked, just how representative and thus useful as a model is the Jersey coast as a case study, given the enormously diverse types of ocean-facing places around the world?
So I think you're asking about the Megalopolitan Coastal Transformation Hub project and why we're repeating this. So I want to bring up, we're not just talking about the Jersey Shore. That's a very narrow set of the coast. What we're talking about, right? There's a reason why megalopolis is in our name, right? We're a sprawling urban mega region. Really, the megalopolis is a name that's applied to the region from Washington up to Boston, but we're focusing on the region from Philadelphia to New York City. And there are a lot of coastal sprawling urban regions around the world. Much of the global population is along the coast. There's rapid development in many regions of the world that is coastal. And so, I think one of the things that I've seen is that core cities have gotten a lot of attention through programs like Rockefeller's 100 Resilient Cities programs and other things, right? So there's talk about cities and climate change, but most of the people in urban areas don't live in the core cities that have a single government. They live in the sprawling, in the sprawl around them, right? Like New Jersey. And so, I think that's really important for us to look at these regions. The Jersey Shore, Port Shore, right? That's interesting, that's useful, but I think it's, we're interested honestly more in where most of the people are in this area. So sort of like, I think we're focused on the urban areas within New Jersey are more promising case studies, and in Philadelphia and in New York.
Yeah, that makes sense. So someone else asked, what is your opinion of geoengineering in this context? Silver bullet or pseudoscientific wishful thinking?
Neither. Right. So let's first of all just define terms. So geoengineering or climate engineering is a term that encompasses a lot of different things. So on one end is what's also called carbon dioxide removal, right? So that's pumping CO2 out of the atmosphere, and essentially trying to reverse what we've done over the last, as I said, mostly the last 40 years, but the last 200 some years. Right, and I think that's that includes everything from expanding forests, which definitely work to the extent that there's land available, to chemical approaches that need work, but if people are developing, I think that's, you looked at what I think, like, if we don't get to net zero by 2050, if we want to hit the international goals, we're going to need a lot of that. So I think that's an important part of the solution. The other side is, includes things like changing the reflectivity of the planet by putting reflective particles in the stratosphere. That is something volcanoes do. It does have a climate effect, a cooling effect. It raises all sorts of governance and ethical questions about side effects of doing it and how do you decide how to do it. It is not something that you would want to do as your first choice. I also am not going to say like it's not something could never, it's never going to happen, and it may not be something you can prevent from happening. If you're, in a state that has the technological capability of doing it, and you're tired of suffering from intense heat waves, maybe you'll just do it because you want to, right? It relates to a whole lot of governance and geopolitical questions. It is not a sustainable solution, right? But it might be something that happens. And then there are other things, people have talked about, like engineering around the ice sheets, which would be expensive and very hard. But I would never say you absolutely can't do it. But it seems pretty impractical based on the analyses that people have done. And so broadly, carbon dioxide removal, almost certainly we need. Making the planet more reflective, we probably don't want to do, but it might happen.
Yeah, that's a very informative response. Thank you. There's one more question. You seem to speak about sea level rising as a given. Mm-hmm. The best we can do is try to mitigate it.
Yeah, so, well, as I said, the rate of sea level rise relates to basically the amount of warming we have. So we can slow it by reducing emission. We can slow it a lot. But we expect to see over the next, if we stabilize global climate at around 2 degrees Celsius, we expect to see somewhere between about 6 and 30 feet of sea level rise over the next 2,000 years. Even though we expect to see probably only about 2 feet of global sea level rise in this century. If we're on a trajectory for 3 degrees, we might see almost double that over the next 2,000 years, and an extra foot or more in this century. Right, so we can slow sea level rise to a pace where we can manage it. We could even conceivably slow it to the extent that where in many places things like wetlands or barrier islands can keep pace with the sea level rise if we allow them space to do so. Right, after sea level has risen on the Jersey Shore, sea level has risen for the last 10,000 years or more, and yet we've had stable salt wetlands here for several thousand years because the rate of sea level rise was slow enough and there was space for them to accommodate. So I was saying we can't avoid sea level rise. It will take thousands of years to equilibrate even to the amount of warming we've already had. But if we have 1,000 or several thousand years to deal with it, we can deal with it. If we heat up the planet enough that we have to deal with 6 feet of sea level rise, not in 1,000 years, but in 100 years, it becomes much harder. In either case, we have to be thinking about the changing climate as we think about the futures of our communities and how we're going to, what we want them to be and how we're going to manage them.
Thank you for that answer. That was very interesting. I'm learning so much in this lecture. Speaking about how much the sea level will rise, I read somewhere that if all the ice sheets and glaciers in the world melted, the sea level would rise like 230 feet. Is that even possible?
Right. Yeah.
But is that even possible? Like, is that a possibility to happen in 200 years?
That would probably take around 10 to 20,000 years, right? So if you think about where is that ice? Well, there's in Greenland, there's about 21 feet of sea level rise worth, mostly sitting above sea level, in highlands. So it's mostly going, when it's up there in the air, it's going to take several thousand years to respond. West Antarctica, there is about 3 to 4 meters, so about 10 feet or so of ice sitting below sea level. East Antarctica, sitting on the continent, but at parts of the continent that are below sea level. East Antarctica there's about another 19 meters, so about 60 feet of sea level rise in areas that are setting below sea level. Those areas are the ones you worry about the most, about losing in time, maybe losing in the course of a millennium or so, right? So that could be 70 feet of sea level rise, in the course of a millennium or less. And then there's East Antarctica as a whole is more like about 50 meters of sea level rise, so much of it above land. So that stuff also is going to take 10,000 years or more to lose. So you're not going to get 230 feet in a humanly relevant time scale. But we could conceivably, if we were on a high emissions trajectory, looking at, say, more than 2 meters or 6 or 7 feet by the end of the century, more than 5 meters some point in the next century. So that would be around 15 feet. That's possible. We're not on that emissions trajectory now. So it would require, a reversal of the progress we've made to be on a trajectory like that. But it is physically possible.
Okay, thank you. Yeah. So I have a question, another question. So what countries are like the most vulnerable to this sea level rise? And what do people in the islands that would probably become uninhabitable in the upcoming decades, what do they do? What do we do to help those people?
Well, so small island states, some of them are very vulnerable and become vulnerable to things like saltwater penetration of their water supplies and more frequent flooding, well before they're permanently flooded. And that's why the small island states are, sort of have a oversized voice and level of activity in international climate negotiations, and have been the ones pushing to limit warming to as close as possible to 1.5 degrees Celsius, 2.7 degrees Fahrenheit. But yeah, I mean, those that in general, when people talk about climate migration, some of the small island states are going to be the clearest places where there is actual climate migration and is very clearly tiable to climate change. There's going to be a lot of climate-driven migration around the world, but except for small island states, the vast majority of that isn't going to be people who can say, okay, I moved because of climate change. They're going to be people who said, okay, I moved perhaps for economic reasons or perhaps for conflict reasons, and those economic changes or conflict changes are happening in a context where they've been affected by climate change. And statistically, us scholars looking after the process and saying, yeah, those economic factors can be tied to climate change, and therefore these people wouldn't have moved were it not for climate change. But when you're talking about small island states, yeah, that is an existential threat to those nations, which is why they are so deeply concerned about limiting warming and find 3 degrees Celsius or even 2 degrees Celsius unacceptable. There's also that's actually not probably most of the people, right? Most of the people are in coastal megalopolises in China and India, where most of the people in the world are. New Orleans, New York, also very, also of a fun region. So, but most of the people are in South and East Asia, where most of the people in the world are. But on the other hand, you're not the sea level rise is not an existential threat to India or to China. There's a lot of Vietnam that's affected, and I don't think it will rise to the level of existential threat for Vietnam either, but it is an existential threat for many small island states.
Yeah, thank you for that. We have a final question before we wrap up the Q&A. Wouldn't it be important to start teaching those things at high and middle schools so we can change people's habits early on?
Yeah, I think it's very important. In fact, I believe New Jersey just this last year became the first state in the country to adopt a K-12 sustainability education requirements. This is an initiative led by First Lady Tammy Murphy. I don't know the details of that. I don't know if they've trickled down to those of you who are in high school already, but I think it is very important. Right. We need education about climate change. We also need good civic education, because as I hit on the point, like, you know, the fundamental barrier to us doing this is not honestly a lack of understanding of the science or the technology. It's the politics and social science and human decision making part of it. And we need people to understand how our country can work, and how a country does work, and how it affects their ability to deal with large challenges.
Yeah, thank you. Thank you so much for this lecture, and so generous for sharing your research with us. As we wrap up this event, as well as the entire lecture series, I would like to say a few concluding words. I'm going to share my screen. When I first started organizing this series with my peers, Ava Ramirez and Grace Boulding, I thought there was no way all these important people were going to agree to come talk to a bunch of high school students, which is why the incredible generosity of these speakers who were willing to share their work and their time with a group of teenagers was so impressive and moving to me. This experience has been truly empowering. I hope this lecture series has galvanized people into climate action by not just inspiring them, but also informing and in providing the proper tools to do just that. Furthermore, I hope this series has recast what can often be an abstract, distant concept, climate change, as a very real, comprehensible, personal, present issue. The lectures brought this issue up close by teaching us about information typically published using specialist terminology in an easily understood form instead. As a result, I hope this series has made knowledge on global warming more accessible to the public. However, this series should have provided enough hope so that the despair is not overwhelming, causing us to repress climate change as an abstraction once again. As Jane Goodall eloquently said, if we all lose hope, there is no hope. Without hope, people fall into apathy. There is still a lot left that is still worth fighting for. This series will have succeeded if it has shown people how to translate this hope and knowledge into the concrete individual intervention that our planet desperately needs today. Now, you may think, what can you do? I'm just a single individual. But what if what my colleagues and I have done has enabled 5 people, maybe 20 people, to learn about climate change and climate action? Then we've done a good thing. If each of those people were then to tell their friends what they learned, the impact is magnified exponentially. Some people might say climate action is only effective when done by big corporations or government, but individual and institutional change are not diametrically opposed. In fact, climate action is most effective when a synergistic relationship between these two changes is implemented. Furthermore, we inevitably demand institutional change through our individual change. More importantly, the lifestyle choices each and every one of us make unavoidably and unintentionally influence the decisions of everyone around you. I am living proof of this. When I went vegan 3 years ago, everyone in my life, ranging from not so close friends to family members, reduced their animal consumption to the point where my parents are almost vegetarians today. Individual change does work because it is never truly individual. In this spirit, I would like to conclude with a passage from Jonathan Safran Foer's wonderful book, We Are the Weather. No one who isn't us is going to destroy Earth, and no one who isn't us is going to save it. The most hopeless conditions can inspire the most hopeful actions. We have found ways to restore life on Earth in the event of a total collapse because we have found ways to cause a total collapse of life on Earth. We are the flood and we are the ark. Thank you for your time, everyone, and sincere thanks once again to our speaker, Professor Kopp. Have a great evening.